Okay, just so you know, you can be thinking about it, we'll talk more about it on Friday, but on the final, there'll be 5 problems. 5 problems. There'll be, now let's go back and look at the first 2 midterms. The first midterm covered chapters 1 through 4. The second midterm covered chapters 5, 12, and 13. So, there'll be 1 problem from chapter 7, which we haven't had an exam problem on. There'll be 1 from chapter 8, which we haven't had an exam problem on. Now we go back and pick up the early material. There'll be 1 from combined chapters 12 and 13, that's radiation. There'll be 1 from conduction, chapters like 3, 4, and 5. And there'll be 1, which is a general type problem from chapter 1 and 2 material. And so we've had problems on those in the first 2 midterms. 5 problems, 20% each, equally weighted. No longer than the midterm problems. So now we've got 5 problems in 2 hours. And the midterm was 4 problems in an hour and 5. So there should be plenty of time to complete the problems, okay? That's my goal, is that there'll be time that you can maybe finish up before the 2 hours is up. Okay, so let me see now. I'm going to give you, of course, your data package again. So you get your data package, the same one you've used for the first 2 modules. You're going to be allowed to bring with you 3 equation sheets, front and back sides, 8.5 by 11. If you want to use the same one you used for the first midterm, fine. The one you used for the second midterm, fine. If those didn't work out, trash and start again. Try the new one, okay? And then maybe 1 for chapter 7 and 8. Okay, so you can bring in with you 3 sheets of equations, whatever else you want to do, example problems, whatever you want to put on there. I'm going to give you the data package with your name on it. Okay, yeah.
Will we be responsible for chapter 6 stuff?
It's wrapped up in 7 and 8, yeah. Yes, you
Okay.
will. The answer is yeah. Yeah. You want to be sure to review that because that's for the basics that are, the basics for both chapters 7 and 8 are in chapter 6, yeah. It's a good point.
Alright.
It's a good point. Yeah. Okay, anything else on that then? Yeah.
Are you gonna post any of like the old ones? Like-
No, you've got examples from old tests on 60% of the final. And I'll tell you right now, the problems of 7 and 8 are going to be like the ones I worked in class, your homework, or the examples in the textbook. They're going to be just like that. Okay. Shouldn't be any surprises. I mean, we went through 7 and 8 pretty carefully and covered all of, we worked 5 example problems in the class. If you go through that, you should be ready for the final. But let's go back and look at 7 again, chapter 7. Chapter 7, mention a couple things. If on your equation sheet you go back to the end of chapter 7, that summary table, table 7.7, it says summary of the correlations for external flows. You don't want to use all of those correlations because they're all not important. Don't forget the rule. Anything that deals with shear stress, or drag coefficient, or force on a flat plate, we don't work those problems. They won't be on the final because that's ME 312 stuff. Okay, so first of all, anything that has equation for shear stress or drag force, don't worry about it. So if I go to table 7.7 and tell you which equations in that table are important, these are the ones that I would make sure are on my equation sheet, besides the other ones I put on the board. Okay. Equation 717, 721, 722, 25, 29, 30, 31, and 44. Out of that table, those are the ones we used in class that I boxed in the board probably, and plus we worked example problems using those equations. Now if I go to the end of chapter 8, there's also a summary table there, which lists probably 12 equations. These are the only ones that are important there for you. And we've covered in class, I boxed them in class, so you know. Equation, this is in table 8.4, page 536. Equation 853, 55, 70, I'm sorry, 57, 58, and 60. There's 5 equations that are important. Plus, there's more than that. It's in my class notes, which you haven't. So, I'm just telling you, if you want to use table 8.4, that's the only ones that are important in table 8.4 to use. Okay, now, let's go back to chapter 7, and I'll tell you which example problems are worth reading and which ones you don't have to read to study the finals. All right, chapter 7. Let's back up to 6 because 6 is part of it too. So let me back up to chapter 6. In chapter 6, you want to make sure you look at example 6.1, 6.2, and that's it. Not 6.3, not 6.4, just 6.1 and 6.2. Okay, so let's go to chapter 7 now and start with the example problems in chapter 7. The ones you should look at, example 7.1. 7.2, 7.3, not 7.4, no on 7.4, no on 7.5, and yes on 7.6, 7.6. Oh, pardon me, that's an X, not a check. No, that's 2 banks, so not 7.6. And that's the end of that chapter. Okay. So you want to study the problems on working class on the board. You want to study the problems worked out as examples in the textbook, and then the homework I assign. And that's the content of chapter 7, 8 on the final. All right, now let's take a look at, that was 7 and 8. Okay, if you came in earlier, I mentioned about the final exam, so if you missed that, ask your neighbor what the story was on the final. Okay. We'll do more about that on Friday, though. Okay, now let's go through where you might stand in the class as of now and project it into where you might end up after the final exam. So we'll do a sample grade calculation. And if you have me for fluids, we've done that in fluids too, so it'll be repeat what you heard me say then. Okay, so let's put down homework scores first. And I'll put down the 12 assignments that I picked up to be graded. I'm just making this up. This is just something I'm making up here. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12 assignments turned in. Full check mark is 1. A check minus is a half. A 0 is a 0. Asterisk is a 0. Okay, so there they are. I knock out 2 of the lowest scores. Okay. I'll knock out that one and I'll knock out that one. Okay. 1, 2, 3, 4, 5, 6, 7 and a half, 8. Homework. 8 out of 10. Special computer problems. Number 1. Number 2. I just guessed, I said, okay, the first one 2, the second one 2.5. So the total on that is 4.5. Now, if you want to check your homework grades, you can do that. I mean, you have all your homework grades. Well, maybe you don't. Because all this big stack here is homework not picked up. It's in my office. The dead homework drawer on my desk. Okay. If you're missing homework, we're going to stop today early to give you a chance to go through all these homework packages to see, to fill in what's up here. Because you might not know where you stand in homework unless you have it back in your hand. Okay, so that'll be Let's end up 10 minutes. Get homework back to you. Also, special problems are in there. Also, exams not picked up are in there. So exams, special problems, homework, in that stack right there. Okay, let's just assume that there's the first midterm, second midterm grades. You have that, so, but I'll assume these first midterm, second midterm. I said first midterm 70, second one went up to a 78. Okay. Now, okay, so I do, what will my grade be if I get a fill in the blank final exam? So you can play the what if game for my final exam. I don't know, I improved from the first one 70 to 78. I'm gonna say, I made a guess, I'm gonna say, I'll take an average kind of. I'm gonna guess I get a 75 on the final. Okay, see what I still. You can do a sensitivity analysis, change that guy to 80, change that guy to 70, and see how your final exam, how your final score ends up. Okay, so your score, and it's on your syllabus, you know, the second page of the syllabus. Homework counts 10 points max. Okay, 8 points. Special problems count 2.5 each. I got 4.5. Each of the two midterms are worth 25% of the course grade, 70 plus 78. The final exam is worth 35% of the course grade. I'm going to guess I got a 75. Okay, so that gives me 75.8. By my grading scheme, that's a C then. Okay, so my course grade will be a C. Don't forget, a C goes from 70 to 78, a C plus 78 to 80, a C minus 65 to 70, and below that, a D or an F. The 65 is a cutoff to go to the next course. Okay, and you can play the what if game. What if I really come in there and, boy, I just get a 90, what do I get? I go in there and I'm gonna get a 55, well, I still pass the course. Well, you can play that game that way. Or you can say, I want to fill in the blank. What final exam grade do I need? This guy said, you know what, I mean, okay, my two grades, 70, 78. I did pretty good on homework, a B minus on homework, and I did a B plus on special problems. So I'm hoping I can get a B out of this class. You say, well, will you take any B? You say, no, I mean, I want a B. I don't want a B minus, that's not a B, that's a B minus. I want the real thing, a B. Okay, you know the result, it's on your course syllabus. B starts at 80, 82 is a B minus, 82 to 88 is a B, 88 to 90 is a B plus. Okay, so I want a real thing, a real B. Okay, I want to, you find what you want right there. If those two midterms were not too good, you might want to say, I want a 65, that's a C minus, I can go on. Okay, put that in there then, C minus. Okay, so now we play this game. Score is equal to, all right, still have 8 for homework, still have 4.5 for special problems, still have the first two midterm grades. By the way, let's put the score in, it's 82. I know I want to get an 82, that'll give me a B. 25% of 70, same thing, 70 plus 78. The final exam is worth 35% times the final. And to do that, I need let's see, 92.9. so you can do that. You can play one of two games. I'm gonna guess my final exam grade, my final exam score, what's my grade gonna be for the course? Or I want this for the course, what's my goal on the final exam? Now, maybe some things are not gonna work out perfect. You say, you know what? My heart's set on an A in this class. Well, you might have some bad news come out of here. If this number is greater than 100, I wouldn't count on an A, okay? Settle for a B plus maybe. You know, some things aren't realistic, so, you know, I know that's what you want, but, you know, it might not happen that way. Okay, any questions on those guys, all right? Okay, how do you calculate your final grade? All right, now, let's go on, and we're going to go back to chapter 8. Let me make some room here. In chapter 8, we have internal flow. We talked about that last time on the board. I put a decision tree on there. How do you get H? For laminar flow or turbulent flow? Turbulent flow is very straightforward. There's just one equation, 860. Laminar flow is more difficult. Is it constant tube surface temperature or is it constant tube surface heat flux? Then the next question. Is it fluid developed velocity and fluid developed velocity, temperature? Okay. Is it fluid developed velocity, not fluid developed temperature? Okay. Is it not fluid developed velocity, not fluid developed temperature? Okay. You go one of three ways in our little decision tree. You get the H. You put the H in the equations to solve for what you want. What do we want? Heat transfer? We normally want one of two things, sometimes both things. Number one, we normally want a temperature somewhere. Maybe the outlet temperature. Maybe how long the tube should be. Calculate L. So typically we want to know the outlet temperature. Or we say, I want the stuff to come out at that temperature. How long must the tube be? That kind of question. Okay. Then we also can ask for the heat transfer. So the two important things in most heat transfer analyses are temperature and the heat transfer occurs. Okay. Some equations hold no matter what. Q equal m dot C to P delta T. No matter what. Laminar, turbulent, fully developed or not, doesn't matter. Other things depend on whether it's constant tube surface temperature or constant tube wall heat flux. So you've got to make sure you use the right equation for that. Okay, so we did all that. We worked two problems, one laminar, one turbulent. In the textbook, chapter 8, example problems, there's two laminar and two turbulent, I think. For homework, I've given you both again, laminar and turbulent, fully developed and not fully developed, so you get to get a flavor for everything. Okay, at the end of chapter 8, there's a section, interesting section, which is titled Heat Transfer Enhancement. Heat Transfer Enhancement, and it's how you increase the heat transfer in tubes. It's titled Heat Transfer Enhancement. So I photocopied parts of that section, so let me give them to you here. Just hang on for a second. We'll get back to it in 10 minutes. Okay. I brought some things that people, our students, who passed ME graduates, and they have you for heat transfer. And sometimes they work for a company that produces heat transfer products. And so I brought a few of these with me. We'll go back to chapter read first, chapter 2. We talked about insulation back in chapter 2. Well, We talked about fiberglass blankets you can buy at Home Depot or Lowe's or some home supply store. There's also pipe insulation. This is like calcium silicate. It's hard pipe insulation. The pipe goes inside of there. Okay. This is block insulation. You can use it to insulate furnaces, something like that. It takes high temperatures, obviously. Trade name is Thermo 12 block insulation. And we can go ahead and put, like we have pipe, the pipe goes in there. Okay. We talked about this last time. We said, you know, if we had a fluid in here and air blowing on the outside, we have convection on the inside, chapter 8. Is the flow laminar? Is the flow turbulent? Is the flow fully developed? Is it not fully developed? Is it constant tube wall temperature? Is it constant heat flux? Then we have conduction through here, chapter 3. The resistance, natural log R outside over R inside divided by 2 pi KL. That's the resistance. The resistance of the pipe right here, same thing. Natural log R outside over R inside divided by 2 pi KL. Convection resistance on the inside, 1 over HA. What's the area on the inside? Circumference, 2 pi R1 inside, 2 pi R inside. Times the convection coefficient from where? Chapter 8. On the outside, air blowing over it, yeah. What's the resistance? 1 over HA. How do you get the area? The area that touches the fluid, air. Pi d circumference times the length, pi dl. And how do you get H? Chapter 7, second part, chapter 7, flow over tubes and pipes. Okay, so this is one of these guys. But yeah, this stuff is hard insulation. You can also have soft insulation, like fiberglass, soft. This guy went to work for a company that made this stuff over in Tempe, Arizona, Arizona State University. So he sent this stuff to me. It's called Thermazip, is a trade name. And you can take this stuff here, and it looks like fiberglass of sorts. It's not. It's just another fiber. But the whole point looks like almost like, you know, again, like duck feathers, like down. Looks like down almost. But the whole point is to trap air in here, so that air gets trapped in here and can't move. And air that can't move, the only way for heat to be transferred is by conduction. So still air is by conduction. So this is a product made by these people. What you do is a bigger pipe. Maybe I don't think I do it. Yeah, I got this thing. Make this a pipe. Okay, here's a pipe. You wrap it around here in the field. This is done in the field. It's patented. You got this little knob here. There. That's all you do. And then this is adhesive. Strip it off. Face it down. Now it's waterproof pipe. Waterproof pipe. It can be done out in the field by maintenance people. It's easy to use. It comes in big, long sheets like this. And you wrap it around the pipe, and then you clamp it down here so it stays in place. So clamp, yeah. And then you adhesive here, pass it down. Now, rain won't hurt it, because if water gets in here, you've lost all the insulation. You cannot have water here. You don't want water in your sleeping bag, in the stuff inside, or you're going to have a tough night sleeping. Okay, so that's, now this stuff is soft like this. This stuff is hard like this. You can't go out in the field and start tromping on this thing. If you do, you crush it. If you crush it, you've lost your insulation, because what have you done? You've forced the air out, and now you've got fibers against fiber without the still air between them. So you don't walk on stuff like this. You could put your foot on here and not hurt anything. This is pretty solid stuff. You know, so it depends, you know, what your application is, but there's different kinds. In your attic, you put up blankets of insulation in your attic. Here's the rule: don't walk on that stuff, because it compresses it. You can blow in crushed up newspaper. They take newspaper, you see, and just shred newspaper, and blow it in your attic. It traps the air. It's wonderful stuff. But don't step off your roof rafters on that stuff, or you're going to crush it. And after time, it settles. And when it settles, you have to start having newspaper against newspaper. Now you've got conduction, you've lost your insulation. So, you know, it's the same old, same old. You hope this stuff springs back to shape if you walk on it. If you step on it, does it spring back to shape? That's a good sign. You walk on it, it stays compressed on the ground, you've lost your insulation. So, by the way, here's another insulation. You know, you just cut it, put your pipe in there. Oh yeah, in your attic, sure. Insulate your hot water pipe in the attic from the hot water heater to the shower, far away. Okay, so closed cell, closed cell. What is this stuff? Oh, there's little air pockets in there, little tiny air pockets trapped in there, trapped in there. They made this stuff. Closed cell air pockets. Air can't move. Oh, good stuff. Good insulation. What? Lightweight? Oh my gosh, lightweight. It weighs nothing. Yeah, lightweight, very important. So stuff like that, you can have closed cell insulation. Blowing in cellulose is paper. Blowing in cellulose insulation. You can also, your pipe fittings. Here's one for a T. Put your pipe in there. There's a T right there. It's made up for you. You put it together. You put something around here to hold it together like that. They make stuff like this for T's, for elbows, and for valves. So in your pipe network, besides your pipe insulation, you have things made, custom made like this for a petrochemical plant, a refinery, a power plant, whatever it might be. And then you've got, let's talk about when we were in chapter 13. In chapter 13, we talked about radiation shields. And we said a typical radiation shield may be composed of 25 to 30 different sheets of aluminized mylar. Here's a little snippet out. This guy was in my heat transfer class, graduated and went to JPL, worked on the space program, and he sent these things to me. Here they are. 25 to 30 sheets of aluminized mylar. Here's another one right here. Okay, aluminized mylar. Okay. Of course, they're all reflective. That's how they insulate in space. They're highly reflective. Called radiation shields. Chapter 13. We had problems on that for homework, and I worked one in class. So, here's a piece of aluminized mylar. This is what the shield's made out of. And it weighs almost nothing. Not even like an aluminum foil in the kitchen. No, it weighs nothing. It weighs nothing. So if you're worried about launching things and you don't want weight to launch, of course you don't want. This is great. It weighs nothing. But you don't just put 28 sheets of this together, because then you have aluminum against aluminum. That's not good. Aluminum's a good conductor of heat. You can't have that happen. You don't want them touched. You want them to stay separated. So what you probably didn't see in here, because you're far away, but if you open it like that, there's, you won't see it here, but there's an aluminum mesh in there. Between every 2 sheets of aluminized mylar, there is a nylon mesh sheet. Nylon mesh sheet. I'm going to show you what it does. There it is. Okay, nylon mesh. They put aluminum, nylon mesh, aluminum, nylon mesh, aluminum, nylon mesh, 25 to 30 times like that. The nylon is not a good conductor of heat. It's a good insulator. And you put it between the 2 aluminized mylar to keep them separated, so you don't have aluminum touching aluminum. So that's one way they do it. Here it is here. There's a nylon mesh. And I won't show you the whole thing, but inside there, it's the same thing done 20 times. 20 times. Between every sheet of aluminum, there is a nylon mesh. Then there are, you can kind of see them, there's holes punched in the aluminum. There's holes punched in the aluminum. Because when the package this in blankets and they launch it into orbit, they don't want the air from the Earth trapped in there. So the holes allow it to outgas. The air escapes into space. And then, now you've got it great. Now you've got no air in here. You don't have conduction because aluminum's not on aluminum. Only way for heat to be transferred is by, chapter 13, radiation to radiation shield. Okay? But there's various ways of doing that. You don't need to put that nylon sheet in there. You don't have to. This is another one with the nylon sheet with the holes in there. You can see how the holes are punched in there. It's punched in the aluminum, so you outgas the air when you launch it. Same thing here. But these guys here, that's nylon sheet, nylon sheet. This one here does not have nylon sheets in it. But it's dimpled. It's a dimpled aluminized mylar sheet. Dimpled. Dimpled. Every sheet is dimpled. Okay? Every sheet's dimpled. Or, here's another one. Nice mylar. No nylon, but there's dimpled sheets in there. Look at from that side, you can see they're dimpled. Okay. They're dimpled. So the way this guy here works is there's a flat sheet of aluminized mylar, another flat sheet, and then these sheets in here, between the flat sheets, there's a corrugated type sheet. And here's the same thing. There's a corrugated sheet. And the only way for heat to be transferred from the hot side to the cold side is at this point right here. Otherwise, the aluminum sheets don't touch. The only point of contact is what? A point. A point. So, my finger, my hand, only point of contact is a very, very, very tiny, tiny area. And what's the conduction? Fourier's law, K, A, delta T over delta X. And what's the area of contact? Oh, it's a very, very small area of contact. So conduction is minimized because they only touch at the dimples. So whether it's this way right here, or this is two corrugated sheets like this one, this is different too. This one right here has little corrugations like that. Every sheet is corrugated. And they only touch at points. They only touch at points. That minimizes conduction, and the only way for heat to be transferred then is by radiation. And when you put 28 shield in here, what does that cut down it by? The denominator is n plus 1. Let's say 29 sheets. 29 sheets, n plus 1 is 30. Cuts down the heat transfer to whatever by a factor of what? 30. 30. Is that effective? Yeah. And what does it weigh? Almost nothing for launch. So yeah, you know, and who does stuff like this? I love these people, but they're not our major. Electrical engineers? I don't think so. Civil engineers? I doubt it. You know, this is what we MEs and aerospace majors do. We design stuff like that. Okay, now, oh, by the way, when you package it, this is what it looks like in the old shuttle bay. This is in the shuttle bay here. This was hanging on the side of the shuttle bay. Here's the grommets, you know, they hang it there. And what is it inside? If you cut open, you'd see aluminized sheets, dimpled sheets like this, 25 to 30 sheets in here. But it's packaged in this thing called a blanket to protect the size of the shuttle bay or electronics, whatever it might be there. You're worried about getting too hot from the sun directly impacting it. So that's how they package the final product. Now we go into the handout I gave you. Heat transfer enhancement. I'll just read the first paragraph. If you want to increase heat transfer in internal flows, okay, here's how we do it. That's the heat transfer in internal flows, chapter 1. Okay. we can't change delta T. It's usually given to us. Can't negotiate that. We're left with two things, H and A. Okay, continue reading. Several options are available for enhancing heat transfer associated with internal flows. Enhancement may be, by the way, this all comes out of your textbook, but I've put it all in one sheet, so I've eliminated some stuff. Okay, you can increase the heat transfer by increasing H, okay, right, or by increasing the area, right, we talked about that, H and A, got it. It says, for example, H may be increased by introducing surface roughness to enhance turbulence. You might want turbulence, because turbulence generally means better heat transfer. As, for example, through machining or insertion of a coil wire spring in figure 812A. So you can insert a coiled wire or a spring inside the tube to increase heat transfer. So let's see if I've got something here. Oh yeah, here it is. What they do then, this is a small example. Here's a spring. They put that spring, for instance, in a small tube where it fits against the inner wall of the tube. It fits against the inner wall of the tube. It looks like the picture I gave you there, okay? It's a spring inserted in a tube. And why? Well, he tells you. It creates turbulence, and turbulence makes better heat transfer. Okay, that's why they do it. What's it like doing? It's almost like roughening the tube wall. It essentially roughens the tube wall because the spring's inside of there. And when you do that, this guy graduated from ME, and he was in my heat transfer class. And I was really lucky. He went to work for a company that did stuff like this. I couldn't believe it. So he gave me all these samples to show people. Okay, here it is. There's a twisted tape and a spring that they put inside a tube. They put the twisted tape and the spring inside of a tube. Wow. There it is. It's an aluminum tube. Crimped, 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 crimped. And a spring thing on it. Why do you do that? Oh, it really messes the flow up. It's no more parabolic. It's not even a turbulent profile. It's some messed up velocity profile. But it mixes the flow. The turbulence mixes the flow, which enhances the heat transfer. And they put that thing in a tube. Boy, it costs money. Oh, yeah. And it's going to create a bigger power demand because it creates more friction and more pressure drop in the tube. So are you willing to pay for the pressure drop to get better heat transfer? Well, that's why you go to college and find out about things like engineering, econ, materials courses, heat transfer courses, fluids courses, because all those things enter into the decision you've got to make about something like this. And then you keep reading. B, okay. We just did A, okay. Alternatively, the convection coefficient can be increased by inducing swirl with the twisted tape. I showed you the twisted tape. The insert consists of a thin strip that's periodically twisted through 360 degrees, introducing a tangential velocity component which increases the speed of flow, particularly near the tube wall. Now he says a third way to do this is to manufacture a tube with grooved inner surfaces. Figure C. Figure C, grooved inner surfaces. There it is. Okay, they put this, they jam this thing, here's a plastic tube. They jam this thing inside of a tube. Think, oh my gosh, were they crazy at the time? No, they wanted better heat transfer. Is there increase in pressure drop? Are you kidding me? Must be a tremendous increase in pressure drop. Are you going to pay for it? I don't know. That's why you have to do your economic analysis and so on and so forth. This is extra weight. It costs a lot more money, but is the heat transfer worth it? Okay. What does it do? Helical. And what are those guys there? They're fins. Those are fins. How do we increase Q? We've talked about in chapter 3. You make A bigger. How do you make A bigger? You attach fins to a surface. There they are. But now notice, the outside of the fins, this is called a fin tip here, touches the inner wall of the tube. The inside here touches the fluid. Okay, so this is your fin problem, combining fin here. It's just jammed in the tube, real tight. It's real tight, jammed in the tube. Introduces a swirl, mixes the flow up, plus it does two things. Mixes the flow up, H goes up. Increases the area, H goes up. Oh yeah, those things are expensive, but they do the job. And then you get to the last one, D, figure 8.4D. He says, you can also increase the heat transfer coefficient by adding spiral fins, which is that one I showed you does. It increases heat transfer that way, spiral fins. In evaluating any heat transfer enhancement scheme, attention must also be given to the attendant increase in pressure drop and hence fan or power requirements. Okay, it's a big, big study, but it's an important study. You want to increase them some more? Okay, take a bristle brush. Something mine isn't just a bristle brush. You clean out your coffee maker with this. I got one office, a little orifice in the coffee. Jam it in there and you clean out the old coffee stuff in there. Yeah, that's what it is. Look at it. What they do is they put this thing in a tube, then they pass the fluid through there. Oh, it increases the area dramatically. It messes up the flow dramatically. It's really turbulence flow. You can't call it turbulent flow because that means something different. It's a flow with a lot of turbulence. Okay, that's what we do. That's not on this picture there. But this guy's company made these too. And then, here's the tube right here. People don't know what's inside of it. They jammed this little bristle brush inside of it. We'll take a normal tube, commercial steel tube. Oh no, it's not. They jammed that thing inside of it to increase the heat transfer. Must have been a good reason, because they did it. Yeah. It increases the weight, increases the cost, increases the power requirement. Is it worth it? I don't know. Run the analysis, find out. We talked about these guys. Chapter 3, under fins. Here they are. Circumferential fins, sometimes called annular fins. Circular fins, the name do the same thing. Fins attached to a tube. It could be a baseboard heater. Some homes have baseboard heating down here. They pass hot water in, heats the home. The hot air rises up the wall by a buoyant effect. It goes around the room, the cold air on the floor comes back down, it's heated, they get a circulation pattern. Baseboard heating, this is not what this is for. Motorcycle engines have this, of course, that's how they cool. But some of these guys, not all of them, some of these guys need, there's a fluid in here, need heat transfer enhancement. So what they do, they jam the bristle brush in there. Bristle brushes are kind of cheap to make. You jam this thing in there. There's a fluid inside, there's a gas on the outside. Water, maybe air, but not water. You wouldn't need this for water, no. This thing here. Here's a cross-flow heat exchanger. Okay? Cross-flow heat exchanger. The fluids in the tubes are here, 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 and here. There's little tiny square tubes in there. They're square shaped. That's why you have to know how to handle non-circular tube geometries. Those are square tubes. The fluid flows from me towards you. The air passes, if it's air, the air passes left to right. It's called a cross-flow heat exchanger. The air and the fluid cross at right angles. Okay. And these are fins. The fins are just wrapped up and down fairly cheaply that way. So it's just wrapped like that. Okay, so fin tube heat exchanger, cross-flow heat exchanger. Just so you know, piece of a solar collector, okay? Obviously painted black, as all collectors are. Black because we're trying to get to a black body. We know a black body is the best possible absorber of energy, so we paint it black. And then, of course, the fluid passes in here, maybe water to heat water for a hot water heater. And then the water in here, define the H, chapter 8. The resistance across the tube itself, chapter 3. The fin surface here, rectangular fins, figure 3, 4. Between the tubes carrying water, which fin model? Adiabatic fin tip, adiabatic fin tip, case B, table 3, 4. Okay. What comes off of this? Well, first of all, radiation comes in, it's absorbed. What goes out? What goes out is convection to the air around the collector and also radiation to the surrounding sky. And where's the conduction go? From the hot fin into the cool water, that way. So again, this is all modeled by what we had this quarter in heat transfer. And then you could have this little guy. These little guys here are like refrigeration type units, you know, maybe there's one in your car for air conditioning. Maybe there's one outside your home for air conditioning. They carry refrigerants. People think those are just plain old aluminum tubes. Oh no, they're not. In those tubes, there's things jammed in there. Those things are jammed in there to increase the heat transfer. Because in your car, you don't have 4 foot by 2 foot for your air conditioning heat exchanger. It's got to be small and compact. It's got to fit in a certain area in front of the engine or in the passenger compartment. So space is a problem. So to get the same amount of heat transfer, you got to do something here, okay? And so what they do there is they make this. It has little, not even square tubes, some oddball shape, radial shaped tubes. Okay, and it's cross flow again this way. Air blows this way. Cross flow heat exchanger. So yeah. And then you've got, maybe it's a trans oil cooler, maybe it's an engine oil cooler, I don't know, whatever. Again, one of our graduates worked for the company that sent this to me. Again, you've got your fluid going left to right, the air going from me towards you, it's a cross flow heat exchanger. Here are all the fins, there's a ton of them. How do you model those fins? Table 3, 4, model B, adiabatic fin. Where's the fin tip? Right here where the wall is. Where's the fin length? Halfway from tube to tube. At x equal L, what's the condition? dt dx is 0. It behaves according to an adiabatic fin tip problem. Oil is a bad heat transfer fluid. Bad. Doesn't transfer heat much at all. But you want a cool oil or trans oil. Not a good heat transfer fluid. They're great what they do, but they're not good heat transfer fluids. So in order to make this thing small enough so it fits in your car somewhere maybe, they've got to enhance the heat transfer. That's what this section is called, heat transfer enhancement. So how they do it? I didn't show you, but there's what they do. They put that thing in every one of these tubes, not here, here. Looks like that. People don't know that. Nobody knows that. Because they don't cut them apart at home and look at them. No, but they're there, they're in there. Why? Because I want good heat transfer in a limited amount of space. So I've got to find a way to enhance the heat transfer. And my choices are H and A. I'll do both. I'll make a swirl, and then I'll increase the heat transfer because these guys are like fins. So I'll induce some swirl, increase H. I'll make A bigger by putting fins in these tubes. Oh, you're going to pay a price on the power. Your oil pump's going to do extra work. Yeah, it'll cost you in gas mileage, of course. But is it worth it? It must be because they're on cars. Okay? So things like that people just don't always understand what's in there. They just think they're aluminum tubes. Oh, no, they're not. Of course your radiator is, because water is a good heat transfer fluid. It's one of the best. I don't want to put fins inside my radiator tubes. Why waste money and weight? No, it's when the oil's in there it's a problem. So, that's when we have to do things that are called heat transfer enhancement. Okay, some big long stories, but some interesting ones. We're gonna stop short today because I want you to pick up your homework, your